verified efficient embedding of a verifiable assembly language.
Hi, thanks for the introduction. So the work I'm going to present today has been done in collaboration with Nick Giannarakis from Princeton University, Chris Habelsel, Asim Rastogi, and Nick Swamy from Microsoft Research, and my advisor, Brian Parno from Carnegie Mellon University. Formal verification nowadays allows us to get closer and closer to the zero defect in programs thanks to powerful verification frameworks. For instance, one can use Coq to write, specify, and prove code correct, and then extract it to verified OCaml or Haskell code. Similarly, one can get verified C# code out of Daphne. But what happens if, let's say, a Coq expert wants to verify code written in assembly or Java or WASM? One solution is to embed these languages in a verification framework as a domain-specific language. Verification frameworks usually provide great support for programmers. First of all, they have precise error reporting, meaning when verification is failing, they report what assertion failed or what condition wasn't satisfied. Second, these tools are usually well optimized so that we can have an efficient verification and a pleasant verification experience. And lastly, they have some valuable features for verification, such as the use of pre- and post-conditions, lemmas, assertions, and sometimes of ghost state or ghost variables. Unfortunately, when embedding a language as a domain-specific language, we lose most of its support. So this yields several interesting questions. First of all, can we make verification-oriented domain-specific languages more efficient by providing some similar support to programmers? Second, could we do this without increasing the trusted computing base? That is, without trusting anything more than the verification tools we were already trusting. And lastly, in the unverified realm, it is common to have hybrid programs that mix several programming languages, think, for instance, about C and assembly. So could we design an interoperation between the host language and the embedded language that would allow us to verify such hybrid programs? In this work, our contributions are the following. We first present techniques to make embedded domain-specific languages for verification more effective, and the crucial point will be that we design a verified DSL-specific verification condition generator. We also develop techniques for verifiably interoperate between an embedded DSL and a host language, and we apply these techniques to both an embedding of x64 assembly in F* and a verified interoperation between assembly and C. And lastly, we build upon this to verify several implementations of cryptographic algorithms. We first present the first verified high-performance implementation of AES-GCM, which is one of the most widely used cryptographic algorithms used for authenticated encryption, and also a fast implementation of Poly 1305 used for message authentication. So our starting point in this work is the Veil framework that was first presented at Usenix in 2017. Veil is a domain-specific language embedded in F* that allows the automated verification of assembly code. And the way Veil works is the following. There is first a model of a machine written in F* that models the state of a machine as well as the machine instructions and semantics. And a programmer can then write some code in the Veil language that allows the specification using a whole logic style. This code will be translated to some generated code that will actually use the machine instructions and the machine semantics. And a programmer can then write a specification for a program that he or she wants to specify in F*. And finally, all of this will be passed to Z3 to F*, which in turn relies on Z3 for verification. And one of the nice things about this approach is that the trusted computing base only consists of our verification tools, namely F* and Z3, of our model of a machine, and of our specification. The Veil tool doing the translation at the top here is completely untrusted. And the reason for that is that what is verified against the model of a machine as specification, and what is later extracted to executable code, is the generated code here in the middle. So even if the translation is unfaithful, it doesn't matter as long as this part is verified. So just a few words about F*, the framework that Veil is using. So F* is a language with an ML-like syntax and higher order logic. It uses SMT solving for verification, and namely the Z3 theorem prover. And it also has support for tactics and for full dependent types. And since it supports full dependent types, it has an interpreter inside the type checker that can perform computations on terms. And where this is useful is that if we consider, for instance, this small function, f, whose signature says that it takes a Boolean as an argument and returns an integer if the argument is true and a Boolean if the argument is false. Type checking the application of this function by, to a Boolean true will be done entirely by the F-star interpreter. F-star won't need to pass anything to Z3 to type check this function dependently. So ideally, what would we want our verification conditions for veil to look like? To explain this, I will consider this small veil procedure called triple. And what we want this procedure to do is to set the final value of the RBX register to be equal to 3 times the initial value of the RAX register. So ideally, we would want F-star to take this program, generate a nice and simple verification condition, and then pass it to Z3. And here, nice and simple means the following. We would first assume the precondition, namely that RAX is smaller than 100, and we would then execute the program written by the user to get a final state. So first, this move instruction, stating that RBX is set to a previous value of RAX, and then there's 2 add instructions that have as a precondition that the addition shouldn't overflow, meaning the sum should be smaller than 2 to the power of 64. Under this condition, we can execute these instructions and first set the value of RAX to be equal to the previous value of RAX plus the previous value of RBX, and then RBX to be equal to the previous value of RBX plus the previous value of RAX. Finally, after execution of this program, we want to prove that the user-supplied post-condition is satisfied in this final state. So this is ideally what you want, but unfortunately, if we naively run the F-star VC generator in our embedding, this is not what we get. And if we just consider this small part of the verification condition corresponding to one of the add instructions, this is actually what we get. And I don't expect you to parse this, it's quite ugly. But the reason for that is that the F-star VC generator is designed for the full generality of F-star. And that means dependent types, and that means higher order logic. It's not well suited for our small, compact, domain-specific language. And because of that, it performs extra computations. For instance, here, it ensures that the RBX register is a valid operand, meaning here that it's actually a register, and this is trivially true. And additionally, we have a lot of details of the embedding that are creeping in the verification conditions. So for instance, here, this eval code function, and more annoying, this register lookups that will then be encoded in Z3 as costly map select update operations. So this is something that gives a big request to Z3, and that will then slow down the verification and make it less tractable. So because of that, we cannot just use naively the F-star VC generator. We have to write a better VC generator. So a first solution would be, let's take our veil code and write our own nice veil VC generator, giving us the verification conditions we want that would then be passed to Z3. But that raises several problems. First of all, that would mean that we would have to trust our generator because we would rely on it for verification. And second, that would also mean that we wouldn't interact with our verification framework, which here is F-star, and we wouldn't be able to reuse the powerful F-star features and libraries. So the better solution that we adopt here is to write our own veil VC generator, but as an F-star program, and to ask F-star to run it during type checking using his interpreter. So F-star will then directly generate the verification conditions we want and pass them to Z3. This VC generator is an F-star program that computes weakest preconditions. It takes some veil code and a postcondition that we want satisfied, and it returns an F-star term corresponding to the precondition that is computed by induction on the syntax. And the important part is that these preconditions are designed so that they can be easily reduced by F-star, and among other things, they are designed to avoid the need for quantifiers instantiations or equality rewriting. So that means that when the F-star interpreter will actually run, it will be able to simplify the preconditions by normalization before actually passing them to Z3. So for instance, this clause that we had previously that was ensuring that a register was actually a register, since this is trivially true, F-star can reduce it to true. And actually, it can simplify it even further because it's a true clause in the middle of a conjunction. So what Z3 gets in the end is a much simpler verification condition, and for this triple case I presented previously, it's actually exactly our ideal verification condition. Another advantage of writing this VC generator as an F-star program is that we can prove properties about it. And the property we are here interested in is that our VC generator is sound, meaning if we take some veil code and a postcondition, the precondition that is given by our VC generator is sufficient to ensure that the post condition is satisfied after evaluation of the code. So this is here a lemma that we prove in F star and that make our VC generator verified and not trusted. And the key idea here is this normalized function that just appeared. This normalized function forces F star to call the F star interpreter whenever we call this lemma. And this F star interpreter has a nice feature, which is that it can be hand-tuned. We can tell it, for instance, that we want to perform specific reductions and to unfold some specific functions. So using this feature, we can actually unroll, unfold our verification conditions and simplify them so that they can have the shape that we want. And what I want to insist on is that this feature is a built-in of F star. We don't need to extend F star in any way to use this. And that means that even using our custom improved VC generator, we do not increase the trusted computing base. We don't have to trust anything more than vanilla F star and Z3 that we were already trusting. Another contribution I want to talk about here is our design of a verified interoperation between C and assembly that allows us to call assembly code from C. So in the unverified realm, it is common to have hybrid programs that mix C and assembly. Think, for instance, of a TLS protocol. You have C code that is quite convenient for writing efficient and low-level code, but unfortunately, for the most critical parts, hand-tuned assembly is needed if you want maximum performance. And those critical parts will usually be the cryptographic algorithms. So here, on one side, we have this Veil framework embedded in F star that allows us to verify assembly code. And on the other side, we have F star that can, under certain conditions, be extracted to C. So we design an interoperation between Veil, our embedded language, and F star, our host language, that allows us to verify hybrid C assembly programs. And this is not without challenges. First of all, assembly and C have very different memory models, and we have to make sure that we reconcile these memory models. Second, when calling assembly code from C, we have several calling conventions that one has to follow and that vary based on the hardware, operating system, and compiler. And these calling conventions specify, for instance, in which registers arguments should be passed or which registers should be saved by the callee. And lastly, since our focus here is mostly cryptographic code, there are several security mechanisms at both the Veil and the F star level that allow us to defend against side channels attacks. So to ensure that our hybrid C assembly implementation will be secure, we have to ensure that these mechanisms compose well. So I don't have time to go over this here, but I refer you to the paper for our solutions to these challenges. To evaluate how well our custom VC generator fares compared to the naive F star VC generator, we compared the response time needed to verify all of our Veil procedures. So on the y-axis, you have the time needed using our custom VC generator. And on the x-axis, you have the time needed using the F star VC generator. So all the points that are below this purple line here mean that using our VC generator yields faster response times than using the F star VC generator. And what we especially observe is that we have an important speedup for the procedures that were previously slow. And that's very valuable because these procedures are the ones that are dominating development time. And the reason for that is that verification is a very iterative process. One has to write code, specification, lemmas, and then pass all of this to verification tools and wait for them to answer. So because of that, if these tools take, let's say, even 10 seconds to answer, that's time wasted for the programmer. So reducing this verification time is quite important. Additionally, since we are writing our own custom VC generator, we can instrument our verification conditions the way we want. And especially, we can embed useful debug information in terms of the source code. So for instance, if verification fails, the error message that will be reported to the user can be something like precondition not met at this specific line of a program you wrote. And that's something that allows the user to track down more easily what failed and how to correct the program. And that's something that, in the end, makes the verification process more efficient and better for the user. So the last thing I want to talk about in this talk is one of the cryptographic algorithms that we verified, and that's AES-GCM. AES-GCM currently is one of the most widely used cryptographic algorithms in the world. According to a recent study by Mozilla, about 91% of secure web traffic uses AES-GCM. And one of the reasons for that is that AES-GCM has very strong cryptographic properties. Namely, it does authenticated encryption with additional data. And This algorithm is so important and so used that Intel actually developed dedicated hardware instructions called the AES new instruction sets so that we could have efficient and secure implementations of AES-GCM. Once it's well optimized, it becomes a fairly complex piece of software that, among other things, relies on modular arithmetic in a Galois field, and that's something that makes it quite complicated to formally verify. So using our improved VC generator, we implemented the first optimized and verified version of AES-GCM. And we compared its throughput with other different implementations. So since we compared the throughput, that means that the higher the number, the faster the implementation is. So in green here, you have several verified implementations, while in red, you have several unverified implementations. Our implementation has a throughput of 1 gigabyte per second. And although it is not yet on par with the best state-of-the-art unverified implementations in OpenSSL, we are several orders of magnitude better than the previous verified implementations in Hackelstar. So to conclude, in this work, we developed a VC generator for an embedded language in a verification framework that's efficient, verified, and supportive of developers. We also designed techniques to interoperate between a host and an embedded language in a verification framework, and use these to verify hybrid C assembly programs. And lastly, we built upon this to verify fast cryptographic implementations written in assembly code of both AES-GCM and Poly 1305. All of our verified cryptography, as well as the Veil framework, is open source and available on GitHub. So if verifying assembly has always been your childhood dream, or you're just curious about it, or anything in between, feel free to try it out. Thank you.
Okay, thank you. Any questions from the audience? We have a question on Slido. How do you compare with the, I don't know how you pronounce this, Jasmine language, which translates to and uses EasyCrypt in the back end to prove cryptographic algorithms?
So if we are talking about the performance of the code that we get, it's a bit hard to compare because our main contribution here is this implementation of AES-GCM that, as far as I know, is not available in Jasmine. Another difference is that Jasmine is using different compiler passes and compiler transformations, while we are more adopting the approach of writing assembly from scratch so that we can hand-tune it as much as possible. So.
Question for Amal?
Could you say something about what sort of restrictions you have on interoperation between your C and assembly or your F star in assembly, and in particular, what sort of assembly you can embed? Is it straight line assembly, or do you allow callbacks? How sophisticated
is the
So
we don't allow callbacks. What we are modeling here is just calling assembly code from C. No callbacks from assembly to C.
Other questions from the audience?
So in the beginning, you said that if I were developing in F# and I wanted to extract something other than C and OCaml. So would this make it easier to say interrupt if I have a sort of a specific dialect of C that I wanted to extract? Would I then follow your approach?
Sorry, could you repeat the question?
So let's say that I wanted to extract Java. Would I then follow your approach the way that you have embedded assembly language, or would I do something else?
It could be an approach. You would have to write a whole domain-specific language to model Java in any verification framework you want. We use F star, but you can do this in Cog, for instance, as well, and then write your own extractor for it, yes.
Okay, we have time for maybe one last question, if we can get to Leonard.
Since you're writing your assembly code by hand, is your code constant time, or do you have tools to verify that?
Yes, so in the Veil framework, we have a verified taint analysis that ensures that all the programs will be constant time. And yeah, that's how we ensure that they are constant time and the assembly implementations are secure.
Okay, great. Let's thank Emeric one more time.